Our group, Debuggers, are going to speak on the topic computer vision. Now, computer vision is a topic that we've all heard of before, but what really is computer vision? Computer vision is the computation of visual objects. Now, visual objects can mean a variety of things: images, videos, icons, and basically anything involving pixels is termed as visual objects. And the computation of these visual objects is what we call computer vision. So when we say computation of images, what does that mean? Computation of images can mean a lot of things. It can mean selecting an object and training it to identify newer objects and classifying them into different categories, or it could mean identifying the different instances of the same object. So in this video we'll be talking about 5 different aspects of computer vision, and then we'll be moving on to the applications of computer vision and its scope in the future. First computer vision technique that we are going to discuss about is image classification. Image classification involves the classification of a set of images into different categories. This categorization is basically based on a number of factors, including image deformation, illumination conditions, background clutter, etc. So the classification of this classification, when it is done manually or in the form of code, it is a very tedious job. So what we do is that we provide a set of examples of each class to the computer, and then develop algorithms that look at these examples, and these algorithms are then able to classify the newer images into different categories. This is the basic principle behind Google Image.
Object detection deals with detecting instances of semantic object of certain class such as buildings, humans, and cars in certain videos and images, etc. Then object detection algorithm typically uses extracted features and learning algorithm to detect instances of an object category. It is commonly used in security, image retrieval, surveillance, and advanced driver assistance system, which is known as ADS. And now let us see some of the application of object detection. The first user case is the face recognition. The popular application include face detection and people counting. Have you ever noticed how face would detect your face when you upload your photos? That is due to face recognition. And this is a simple example of face detection that we can see in our daily life. Even DSLR camera and phone camera uses face detection. Object detection can also be used in people counting, that used for analyzing crowd statistics during festival. Then object detection also used in industrial quality check. This is one of the most recently and interesting application of object detection, which is the self-driving car, and it sends the people on the road on its way and it automatically stops. And the final use case is the security, which is used in banking as well as in phone industry. In banking, it is used to identify the fraud and forgery of notes or currency, and also theft. Then another important application is face recognition, that is used in smartphones, and which is also known as face unlock. Now we understood the application of object detection. Then let us look the workflow of object detection. It involves 3 steps. First one, we have training data, which should input and create our model. Now this model is created using visual features, which is abstracted from the images or the digit or whatever be our input. Then upon extracting these features, we have a classification model created. After that, we have testing data in our final post-processing step.
Object tracking. The basic principles of object tracking are based on the online version of the AdaptBoost algorithm, which uses a cascade hard detector. This model learns from positive and negative examples of the object. A user or an object detection algorithm sets a bounding box, a positive example, and image areas outside a bounding box are considered as a negative. On the new frame, the classifier starts in the surrounding area of the previous location and forms an estimate. New location of the object is where the score is maximum, thus adding another positive example for the classifier. The classifier updates with each new frame arrived. Kernelized correlation filters is a tracker with high accuracy and speed. It uses samples from the original positive example area and then form a mathematical model for overlapping sections for initialization. The tracker can repeat the detection of objects through a fixed period of time to improve accuracy and reinitialize. To calculate motion characteristics, it is necessary to convert coordinates and trajectories from video coordinates to coordinate of a real scene with the help of homographic transformation. For sports analysis applications, for example, the real scene is a description of a playing field and its dimension. This description is translated into a field model which is analyzed on video frames. A field model is a set of zoning lines and their intersections. The Hoare transform method is used to search for these elements. Next, we compare the found lines with the field model, select the corresponding points and calculate the projection matrices with which we transform the screen coordinates into the coordinates of the field model. If some matches are inaccurate, then one of the three robust methods, Randsack, LMETS and PHO are used. They try many random subsets of the corresponding pairs of points, evaluate the homography matrix using a subset and a simple least square algorithms, and then calculate the qualities of the resulting homography. The best subset is then used to obtain an initial estimate of the homography matrix, and finally motion characteristics of objects were calculated based on the trajectories and coordinates of objects from the playing field model. And of course, in order to capture a good quality video, it's better to shoot with stationary cameras. If records were made not from fixed cameras, then it's necessary to remove jitter and displacement effects. In this case, we need to use motion compensation with optical flow.
Image segmentation. Image segmentation is a task of partitioning an image into multiple segments. This makes a whole lot easier to analyze a given image. This is quite similar to grouping pixels together on the basis of specific characters. Now these characters can often lead to different types of image segmentation. Usually image segmentation is of two types. One is semantic segmentation, the other is instance segmentation. So semantic segmentation. Semantic segmentation is a task of assisting a class of every pixel to a given image. That is, for example, in the given figure, we can see a building, a sky, window, door, car, and vegetations. These are all together. Like, for example, there may be many buildings in the figure. So all these buildings come under one class name as building or build. So, for example, if the doors of many buildings come under one class, that is doors. So, etc. Vehicles, or many cars may be in the figure, for example. So these come under one segment called vehicles. So in these cases, this is called semantic segmentation, and all pixels belonging to a particular class have been assigned to a single color. If we come to the examples or the application levels of semantic segmentation, one is self-driving cars, which are going to be the future of vehicle system in all over the world. And the second one is portrait mode in your phone. Example, in iPhone and the latest upcoming phones all have a feature of portrait mode. The portrait mode actually works on this key. It focuses on the main object, which is when you take a photo of yourself or you take a photo of a flower. The camera focuses fully on the flower and the rest of the parts are blurred. So the focus is based on this semantic segmentation process. In the second example we have told is self-driving vehicles. Self-driving vehicles focuses mainly on segmented images, that is, it is used to navigate the routes. The self-driving vehicles uses the camera in front to find out how the road is, to find the measure of the road, how the car can fit inside one track and how it can move to the next when the speed is lowered. Through these features, that is computer vision and semantic segmentation. And the second type about segmentation is instance segmentation. In instant segmentation, as we were told earlier in semantic segmentation, that a group of people standing are, taken as under one class named people or humans. Whereas in instant segmentation, every human being is segmented into different class. That is, the first person is segmented as person 1, the second as person 2, and so on. That is the main difference between instant segmentation and semantic. An application level of instant segmentation we can call is the group feature that's in Samsung or any other mobiles, etc. The group fee selects every part of the people or the person standing in a group photography, and the camera focuses on every person's face using face recognition. So this is a method of instant segmentation.
Now let's discuss about the various applications of computer vision. Computer vision is an emerging technology that is embedded in different devices we use in our daily life. For example, we can find it in any of the multiple cameras in our mobile phones, tablets, or photo cameras. It is also in the games of play. In identity-based access control systems, our support to medical diagnosis, and surgery assistance, and for smart interfaces among other industrial sectors. Computer vision deals with the problem of understanding automatically image or video content. This is an ability we humans perform in almost unconscious manner, but it is a big deal for computers. Object recognition, or the automatic identification of objects such as pedestrians, cars, movement analysis, or the automatic identification of actions, and 3D reconstruction, or the automatic extraction of 3D information from videos or images. A lot of new software or hardware engines will come out to be integrated in new smart devices such as smart glasses or smart cars that will run in our roads in the near future. So far we have discussed about the 5 major computer vision techniques that will help a computer extract, analyze and understand the useful information from a single or a sequence of images. There are many other advanced techniques like style transfer, 3D objects, action recognition, colorization, etc. Now let's see what will be the future of computer vision technology. With further research on and refinement of the technology, the future of computer vision will see it perform a broader range of functions. Not only will computer vision technologies be easier to train, but also be able to discern more from images than they do now. This can also be used in conjunction with other technologies or other subsets of AI to build more potent applications. For instance, image capturing applications can be combined with natural language generation to interpret objects and surroundings for visually challenged people. Computer vision will play a vital role in the development of artificial general intelligence and artificial superintelligence by giving them the ability to process information as well as or even better than the human visual system. Considering the capabilities of present-day computer vision, it might be hard to believe that there are more benefits and applications of the technology that remain unexplored. The future of computer vision will pave the way for artificial intelligence systems that are as human as us. However, before doing so, there are a few challenges that must be overcome. The biggest of them being the demystification of the black box of AI. That's because, just like other deep learning applications, computer vision, while being functionally effective, is undecipherable when it comes to its inner workings.